Is that working? That looks like that audio is working. Okay. Cool. All right. So we're looking at ethers and thiols and things like that. For the most part, we're going to treat them like they're acting like alcohols, right? So that means they can act as nucleophiles. So SME is really just the same as methoxide ion. We're just going to treat it the same way. We use that as the nucleophile. The sulfur will attack. So for this first one, step one is what? Epoxidation. So we make ourselves an epoxide, and then steps 2 and 3 are Grignard reaction, and then neutralization. Right. So which sides are epoxide is going to look like? Look like this, and then we're adding a methyl group as a Grignard reagent. Which carbon is the methyl group going to attach to? Carbon 1 or carbon 2? Carbon be the more substituted, because with these epoxides, because of the strain energy, it's not going to go for the less steric leader, it goes to the more substituted, because this carbon oxygen bond is weaker. The more substituted carbon oxygen bond is weaker. So we wind up with OH here, and we added a methyl group there. B is a bit of a throwback. Oxymercuration with the methoxide as our nucleophile. So oxymercuration was a hydration and it was Markovnikov. We're not adding an OH group, we're adding a methoxy group. We need more substituted carbon. Maybe. I honestly don't remember.
Yeah, right. I don't think that one was.
I think C might have been, because that was one that I had a question about, the NASME. That was one of the quiz questions.
Okay, yeah.
But we'll get to that.
Let's do it now. If nobody has any questions about B, we all go with that one.
Yeah.
All right, so for C, we do epoxidation again. So we have the same intermediate. And then our nucleophile, instead of being a Grignard reagent, is a sulfur methyl group. So we're going to make ourselves a thioether. So if we break this apart as an ionic compound, we get Na plus as one of the ions, and then we have S and E with a negative charge on the sulfur. So, and just like before, with all these ring opening reactions, we go to the more substituted carbon. Not technically considered Markovnikov because it's once it's a 3-sided ring, it's not an alkene, and Markovnikov's rule only applies to alkenes, but it's a similar concept. The second thing that gets added to the more substituted carbon.
Not pretty two oxides, one from the other.
Yes, I guess we'll get this plus En, which means we're going to get started drawing the oxygen up, then our SN2 has our new methyl group going down, plus EN, good call. And then same thing here, so this, in both cases, carbon 1 is not a stereo center. But carbon 2 is.
Yeah.
So again, the way we drew it. That would mean. From this intermediate, we would get this, and then we would also get the enantiomer. So in this, it doesn't really matter because it's not a stereo center, if we're being careful showing. It would be, the oxygen would be up because this is an SN2 step, the ring opening step is SN2, so it's coming from the opposite side. But it doesn't make a difference, I didn't want to confuse which enantiomer we were talking about, because having 2 other hydrogens attached to it means it's not a stereo center.
But they're not going to be both pointing down because of the SN2.
Right, one will be that way. One will be in the plane facing that way. Based on what we had drawn before. Jerry, did that address your questions about this one with the NASME?
Yes, actually, oh, I forgot, it was number 6 on the first question that I really had a.
Okay, let me pull up the quiz and we'll talk about that one.
Yeah, it's the same one.
Oh, it's the same, yes,
C.
oh, it's.
See? Okay,
Or, yeah,
oh, E,
yes. The side.
Yeah.
okay, so. Do you want to start with your question, or should we work through it and see if it answers your question?
I was just confused about,
Okay.
especially the second step, I don't remember seeing that.
So in this case, so for. A and C, we made the epoxide ourselves, and then that was the target. Here, this. Tells, we're making our nucleophile. And then exposing it to the epoxide, so we just switch the steps basically. Because what does step 1 do? Yeah, it just deprotonates an alcohol irreversibly because it makes the hydrogen gas. So that means that we're gonna have. There's our nucleophile, and here's our epoxide. So it's still just a ring opening reaction, we just switch the order of the steps.
Okay.
So then, as before, SN2 comes into the more substituted carbon. Break that bond. So we're gonna wind up with. And then. Messy, basically funny direction, but. We're gonna have a cyclopentoxy group. And no stereocenters. 2 hydrogens that are identical here, 2 methyls that are identical here. And the last carbon we might consider is symmetrical both directions around the ring. So no plus again here. That cleared up? Okay. Any other questions related to the quiz specifically? And turning sets.
Nope, wrong one. Did I catch it in time? No. No. Wi-Fi is really slow right here right now. All right. So starting from an epoxide that has stereochemistry, we just have to be careful to keep that stereochemistry the same and pay attention. Remember that with these ring opening reactions, the second step is always going to be an SN2. And sometimes the first step if it's under basic conditions. We're under acidic conditions here. So what's the first step? Draw the bonds that have to be formed here. So yeah, proton transfer. So that gives us an intermediate that looks like it's just the same. Same molecule, protonated, and generated our nucleophile while we're at it. So the bromine is then going to act as the nucleophile. And again, the bromide is going to wind up on the more substituted carbon. Just make sure you draw both of your arrows there. So everything's going to stay more or less in the same position, except that instead of being sort of like flat, they're going to kind of pop upward. So we're going to wind up with, there's our carbon and carbon, our OH up, a methyl forward, and a hydrogen back. Now on the other side, we get our phenyl group up and into the board, our ethyl group up and out of the board, and our bromide down to the left. So 180 degrees from where that oxygen was, right? Coming in from the opposite side. The nice thing about all these ring opening reactions, yes, we have to consider stereochemistry, but it's really not a whole lot different than the bromination, than the dibromination, or the oxymercuration that we've seen in the past. You make a three-sided ring, your next step is almost always going to be a ring opening reaction. And it pretty much always goes in the same pathway. Nucleophile attacks the more substituted carbon. All right, how we feel about this? Yep. And that's, you know, honestly what separates the, you know, the, I don't want to say the A student from the B student, because it's not necessarily the case, but like the student who's really understanding mechanisms and thinking about the whole way through, we really want to be thinking about these as three-dimensional objects. So it's not just where you're drawing the arrows. It's also, are you thinking about, okay, which side is this coming in from? Right, I could have just left the bromide here and drawn the arrow there, but that would have been confusing, and you're going to lose the stereochemistry if you do that, right? So try to think in 3D as much as we can, but that's just something that comes with practice. It comes with more experience. The more chemistry you take, the more you'll get used to that, the more it'll kind of make sense. And play more video games. All right, let's.
Next question about that last one.
Yeah.
If it was fully substituted, if the carbons were fully substituted, then would it?
I believe so. Then it might come down to. I think in that case, you're gonna get a mixture of products, but I think you're gonna predominantly favor the one. Your addition is going to happen on the more sterically hindered, which seems backwards. But because it's that three-sided ring and it's so strained and kind of planar almost, sterics don't prevent the SN2 attack as much as they strain this bond. So I think you'll probably wind up, like say if it was two methyls on this side, they're both tertiary carbons then. But this one's a little bit more crowded, which means this bond is weaker. And so it might be something like a 60-40 ratio or something along those lines where you'll get a measure amount of both, but in general, your major product is going to go towards the more sterically hindered one. Because that means this bond is weaker.
It is counter to.
It is, especially when we started with SN2, right? But I remember our original SN2 mechanisms didn't have that strained bond that we were breaking. And with the strained bond, with it starting so high in energy, that bond is so much easier to break. And that allows the rest of this stuff to get out of the way and act more like it's planar almost. All right. So this also means we're getting ready to start our last chapter. We're making good time. We haven't had many snow days and we've been moving at a pretty good clip through these, which means we actually take a little bit of time to catch our breath, catch up on anything that we have for these next couple of weeks. I would say I haven't looked at the weather forecast for today or from today yet, but it looked like we might have weather coming in Wednesday night. So we might not be meeting on Thursday morning based on weather. So it's good that we have a little bit of a cushion here. And it's also good because since the midterm, this next chapter is going to be the trickiest because it's the most different than any of the mechanisms we've looked at before, because we have to go back to talking about orbitals again. Which I enjoy, but it's a heavy lift because we've just gotten into the zone of let's crush through a couple new mechanisms that all look the same as old mechanisms and move on. So we're going to talk about dienes at this point. And dienes have a couple different classifications, and dienes just what it sounds like. It's when you've got two alkene bonds, two alkene groups in the same molecule. It's not the same as aromatics. So benzene rings and other aromatics are not the same as dienes. They look really similar, especially for some of those 5-sided rings that we talked about last Thursday, like thiophene. That seems like it's a diene. But having that extra lone pair on the sulfur means it actually behaves more like a benzene ring than it does anything else. And so a diene specifically means only two alkenes and no resonance beyond that. If you have two alkenes attached to the same carbon, that's pretty uncommon. But if you do see that, it's called accumulated diene or an allene. But those are pretty uncommon, as mentioned. Conjugated dienes are more common because that conjugation means we get resonance stabilization. And that's actually what we're gonna look at for our primary reactions from this chapter is gonna be with conjugated dienes. And then last but not least, or maybe last and least, isolated dienes means that there's no resonance, but that's an advantage there in that it means that they just behave like an alkene group just twice. So they'll go through all the same reactions that an alkene will, you can just do twice. And if you don't have enough stoichiometry, you don't have enough reactants to do it twice, and you'll get usually a 50-50 mixture of which of your alkene groups reacted. Maybe a little bit off depending on sterics and things like that. So isolated dienes aren't really that interesting, not enough to have a whole chapter dedicated to them. Accumulated dienes are really uncommon and unstable. So most of what we're going to spend our time on in this chapter is the conjugated dienes. All right, so one of the ways I can ask about this is just, classify them. Are they accumulated, conjugated, or isolated? This isn't a diene, but if we were saying that double bond right there, would we call that accumulated, conjugated, or isolated? Conjugated. It's just conjugated with carbonyls, not conjugated with another alkene. Incidentally, this is what we ran into last week. It wasn't this molecule exactly, right? But we ran into an alkene that was conjugated, and that caused a problem with our reaction, right? Because that conjugation gives us extra stability. How about this? You got one that's isolated, but those two are conjugated. Same here. Those two pi bonds are conjugated with each other. That one's isolated. Really, the way to separate it out is there an sp3 carbon in between them? If there's an sp3 carbon in between, then you can't have any resonance. If it's a lone pair, if it's a nitrogen or an oxygen, that gets a little bit hazy, right? Because a lone pair can participate in resonance. But if it's sp3 carbon, there is no lone pair.
But that's like conjugated next to something.
So if we put an oxygen there, that whole system is now conjugated. Because that double bond is conjugated with that lone pair, which is conjugated with these double bonds. How about carbone here? Conjugated and isolated. This is the one where the mirror image is responsible for the flavor of caraway. Spearmint and caraway don't seem that related. They don't seem that close, especially because they're used in such different contexts. We're used to spearmint as being more of a sweet. But they actually do, if you smell them side by side, you can say, oh, actually, I can see how they're a little bit related. And but it's just that carbon being flipped gives you S carbone, which is caraway. All right, so if we want to make a conjugated diene, we do a double elimination like with alkyne, but we do it with a sterically hindered base and not with sodium amide. Remember, we had to get that double elimination and to deprotonate the alkyne, we stuck with sodium amide because it was an even stronger base. If we use a base that's not quite as strong and sterically hindered, when we go through a double elimination, we'll get a conjugated diene. And it will, even if there were some more carbons on either side, it'll still favor making the conjugated example. So for instance, if we had. If we had this molecule, these two bromines aren't quite as far apart. And we would think, okay, sterically hindered base, that favors making the Hoffman product, right? So that would, if we didn't consider resonance, we might think or expect our product to look like that. However, because we get extra stability by having these two things be conjugated with each other, it'll actually preferentially make this molecule instead. Even though that's not what we would expect based on Zaitsev's rule. And then the other way you can do it is you can also just force an elimination with, if you already have one alkene, if you can get a bromine anywhere near it, you can do another elimination, right? It doesn't have to be both eliminations in one step. If we're doing this as a synthesis problem based on your starting material, you wound up with something like this, or even with the bromine one spot removed from the allyl position. Forcing it to go through an elimination again with a sterically hindered base will also give you your conjugated dye.
Would that be a mixture or would it just?
Shouldn't be, well, in this case, there's no other carbon, but if it was a case like this. If we were looking at. That guy, it's gonna favor making this pretty strongly. The difference in energy from having these isolated, I actually have that on the next graph. Having isolated alkenes versus conjugated alkenes is a 15 kilojoules per mole difference, which is relatively significant in terms of equilibrium constants. I don't have the numbers right off the top of my head, but it's gonna be like it might be like 100-to-1 ratio, depending on your temperature. But you're gonna favor making the conjugated one pretty strongly. And this is the way that they get that answer or that number is they just hydrogenate a isolated alkene. In this case, two different molecules, but they did the same thing. They could have used that molecule isolated versus conjugated, and they would have gotten the same answer here. They just looked at the energy of hydrogenation. And so we do see it's still not, that's pretty downhill in energy in both cases, but 15 kilojoules per mole difference can be pretty significant. Because remember, we do have our equilibrium constants are that E to the minus delta G over RT. So 15 kilojoules per mole difference in the exponent of this function, that's relatively significant. All right, and the other thing about having these conjugated is it actually means that this sigma bond in between the two groups doesn't have free rotation like we're used to with sigma bonds. Because if this rotated around, we'd actually be breaking that pi system. Right, if you look at the way that the resonance structures look with these pi orbitals, the most stable state is when with these conjugated, the whole reason we get that bonus to the stability is because that allows all of these p orbitals to line up together and be in phase and spread those electrons out a little bit more, aka make a better resonance structure. If we twist this so these orbitals don't line up anymore, we're breaking that resonance. So if it was 15 kilojoules per mole difference to hydrogenate, to go from conjugated to isolate, which is effectively what we're doing by rotating that. We can expect that there's gonna be a barrier of about 15 kilojoules per mole to rotating around that center bond. Even though on paper, it looks like it's a sigma bond, like it's just a sigma bond, it's it's not sp3 because they're both sp2 carbons. Even though it looks like it should be rotationally symmetric, the resonance structure here, there's gonna be two resonance structures. So if we do a resonance structure where those electrons come over and these electrons move there, we get a negative charge, double bond, positive charge. Right, or and then there's also a resonance structure where that goes the opposite direction. Which means, so neither of these is as stable as this. This is the major resonance contributor, but they're both valid resonance structures, which means that's part of what's causing that conjugation to be more stable. And if you rotate, that breaks the pi bond. So it's not as much as rotating a full pi bond, but you get a similar effect as far as it being a hindered rotation. Which means it's gonna predominantly stay in one of these two conforms. You're not gonna see it, there should be a transition state in between them being the cis conformation and the trans conformation. Right, because taking this and rotating it up, we actually might do a computational lab where we calculate that potential energy surface next quarter as one of our labs. But taking this and just rotating it so that it's the S cis turns into the S trans is gonna have about a 15 kilojoules per mole. Very. And try and drop this into the scale. So out of these, which would we expect to be more stable out of this S cis? And when they say S cis versus S trans, it just means we're talking about the sigma bond. That's what the S is signifying. So would we expect the S cis or the S trans to be more stable? Why? Sterics. Yeah, all the things. The electrons all look the same, the bonds all look the same, you still get the same resonance structures. But having two methyl groups pointed the same direction means you've got a little bit of an eclipsed issue going on, to go back to our cyclohexane examples. And so we would expect the S trans to be a little bit more favored. But not by a ton. By, one carbon eclipsed sterics, which if you remember those similar graphs that we looked at back from talking about cyclohexane. I want to say that a carbon, like two methyls being eclipsed, was something like 3 kilojoules per mole. Maybe, I think it was single digit kilojoules per mole. So it's actually a larger barrier to break that conjugated pi system than it is any sort of benefit that you get. Also worth noting though that at room temperature, the rule of thumb in my computational chemistry group in grad school was that any reaction that has a barrier of 100 kilojoules or less, you can consider that to be happening in a reasonable amount of time at room temperature. So with this only being 15 kilojoules per mole barrier, we're at equilibrium. It's not enough of a barrier at room temperature that you would actually lock it into one of these. That actually, it's 12 kilojoules per mole difference. So I actually was pretty close to being to scale. 15 kilojoules per mole to break that barrier. We gain 12 kilojoules per mole by not having that eclipse, those two methyls eclipsed.
It's like you might have drawn it better the first time, or you erased there.
And they have. Um. And obviously, these numbers are gonna change a little bit depending on. If it's two hydrogens and two methyls, or if it's. You know, if there's larger groups attached, it's gonna look a little bit different, but that's just to get a general gist of what's going on. We're going to favor the state that allows us to minimize. Sterics. Okay. And if we compare that to rotating that same carbon 3 to carbon 4 bond when it's not isolated. We only see a barrier of about 5.6 kilojoules per mole. So it is significantly larger barrier. All right. We've got 15 minutes left. We okay pushing through since we started late, not having a break, and then we'll take a break before lab. Okay. Just some other kind of review ideas. When it comes to orbitals,
That's totally off.
that is totally off, isn't it?
It's 11:10.
It's 11:10.
I was about to say.
All right.
Still go.
Well, I didn't get a break between my meeting and now, and I have to use the restroom. So let's take a quick 5-minute break. We'll make it a short one today. Come back in 5 minutes. Or hang out.
Oh, yeah. 3 minutes next up. Sorry. Oh, I heard y'all talking about IVs last Tuesday.
Yeah.
I was, I've, when I have like a cold or something, when I work something out, I'd always have a bag, you know, so I would just start an IV in my thigh right here, and then hang it up on like a perker rod or something, and just sit there and like rehydrate. And the only negative side effect that you really gotta watch out for, like if you're doing that with a patient or whatever, is fluid overloading, because then it goes into the lungs and you get pulmonary edema. Cause it like flushes out kidneys, it flushes out liver, like it's great for that, so just like, here's a bunch of water, like, let's just move stuff.
Right.
Those organs like movement, but yeah, it's a fluid overload. I've had that one time where I did like 2 liters instead of 1, because I was like really hungover. Back when I used to do that, and so I was just like, oh, it's kind of short of breath. Okay, let's just stop that. You know?
Do you ever try the chelation therapy ones though?
No, I really don't know anything about that, other than, like, they do that in Arizona, they are super lax with a lot of their stuff, they're like very progressive as far as like they let EMS do. And so there's a bunch of companies that will just like pay a bunch of money, and then the medic shows up, it's like Shill's job as a medic, you just.
It's nothing wrong with anybody, just somebody's hungover and they want.
Literally, yeah, that's like 90% of what that is. Or it's like Jeff Bezos wants like the blood of the young.
Yeah.
Something like that.
Like, sure, if you got a bag for it, I'll run a line. All right, let's talk a little bit about some molecular orbital review. It's something that you probably saw, we talked about this a little bit in OChem 1, back before midterm, we were first talking about orbitals in general. But remember, this is partly a reminder that the way that these orbitals work, the way that we get bonding happening in general, is we have to be able to take 2 orbitals of a similar shape and phase and get them close to each other in order for them to overlap a little bit, and then we can kind of combine their function and, you know, basically do like a weighted average of their functions, mix them together to get a new orbital that's going to be lower in energy than either of them separately. So this energy scale here is looking at versus having 2 isolated p orbitals, 1 electron in 1 p orbital, 1 electron in another p orbital. By allowing those to get close enough together to form a pi bond, we get a lower energy as a result. So these bonds are always as a result of mixing together 2 functions in a way that lowers the overall energy. This is true of sigma bonds too. Right, a sigma bond, if you have an sp3 hybridized orbital, it kind of looks like a balloon, right? With a little bit of that figure 8 piece on the other side. If you have 1 electron spin up there, and then you bring it up to another sp3 orbital, they should be the same size, but I just messed up drawing. When you bring them together, the sigma bond is actually what you get when they overlap with each other. And so we'd have a similar sort of situation here where we have, you know, an sp3 and an sp3. And by bringing them together, we get an overall decrease in energy that looks like a sigma bond. That's going to look like this sort of in phase overlapping of these 2 big portions. Right? But that means that every time you form a bond, whether it's a sigma bond or a pi bond, there's also the opposite possibility. If you try to make these line up when they're out of phase, instead of getting constructive interference that gives you this sigma bond shape or this pi bond shape, you can wind up with them making an anti-bonding orbital. Bizarro bonding orbital, basically. When they're completely out of phase, you get the opposite of a bond. What's the opposite of a bond? Well, an anti-bond. That's literally how the thought that went into naming this. It's the opposite of a bond. And every bond that you form has an anti-bonding
orbital that's corresponding, it's usually. And if this is symmetric, not all, these aren't always symmetric energies, depending on if you have two different atoms, one of them might be higher in energy than the other. But they're always gonna combine, make one lower in energy and one higher in energy. And the simplest way to think about it is them being symmetrical. And as long as both of these are carbons, then they will be relatively symmetrical. In this anti-bonding orbital, usually we don't put electrons into it. Because if you have one electron coming up from one side and one electron from the other side, that's two electrons that are going to participate in this bond, right? They're going to fill the lower energy slot. So one of the ways that reactions happen, when we start thinking about things like that, like an SN2 reaction even happening. An SN2 reaction, we're breaking a sigma bond to form another sigma bond, right? But part of the reason it has to approach from the opposite side is that you have to start putting electron density into the anti-bonding orbital. And the anti-bonding orbital of this sigma is going to look like basically like two figure eights where the phases alternate. So if this one is shaded, this one's not shaded, this one's shaded, this one's not. You break a sigma bond by bringing electron density and putting it into the anti-bonding, which is 180 degrees in terms of direction from the bonding orbit. So we didn't really need that level of detail to explain SN2 reactions because just sterics is kind of and partial charges was enough to think about that. But this idea of bonding and anti-bonding orbitals applies to every reaction, every bond that's being broken or formed has some element of let's bring electrons into the anti-bonding. And that's part of the reason why transition states by definition are higher in energy, is because you've got to move electrons into those higher energy anti-bonding orbitals for the bonds to break. Right, as far as it applies to our dienes here, we're mostly going to be talking about pi bonds when we're talking about dienes. The same general gist, right? If our bonding orbital is when you've got two p orbitals that are in phase with each other, so the red is matched with red and blue with blue. And color or shading are the most common ways to indicate phase. We don't want to put charges to it, like a positive or a negative. It behaves like positive and negative. Like if you put a blue orbital and try to overlap it with a red orbital, you'll get destructive interference, like they're opposite signs, because they are opposite signs, but we don't want to put a number to it, positive, negative, because that implies charge. And it's a totally different variable, which is also why we have spin up and spin down, because we don't want to say positive spin and negative spin because that implies charge. So it's just different variables that have positives and negatives that we indicate with different ways. So shading and color is the most common way for phase. And so when we have them lined up properly in phase, we get the constructive interference and get a pi bond forming. When you bring the two p bonds that are out of phase together, they push each other away. You get this sort of clover look. Right? So if we want to break a pi bond, one of the ways you do it is by bringing electrons into this anti-bonding phase. And that's also partly what happens when you start rotating these. And what you'll notice, the other thing you'll notice is that for a bonding orbital versus anti-bonding orbital, you're always going to be adding one node to go from a bonding orbital to an anti-bonding orbital. So here we have one node, and that one node is where the sigma bond is, right? Which works spatially because that means we're not trying to put too many electrons in the same spatial area. But it does have one node here. The anti-bonding orbital has two nodes. We added a node across where we had constructive interference. Now we have destructive interference. Right, and the same is true here.
if I was being really careful and showing all the electrons, there actually is a little bit of the out of phase. That's basically this piece. It's still there, it's really small once you mix these together. So in this case, we have 2 nodes and we add a 3rd node to get to the end of bonding orbital.
Well, as far as adding electrons into the anti-bonding orbital for like an SN2, they're coming from an external source, but it can't, like, with a radical reaction also be just increasing one of the like internal electrons to that higher energy.
So, and that's one of the ways that you get a homolytic cleavage. The reason that light is a common catalyst for those is to get a homolytic cleavage. The easiest way to do that is to promote an electron from the bonding orbital to the anti-bonding orbital. Because when you have an equal amount of electrons in a bonding orbital and an anti-bonding orbital, they cancel each other out, and you have net no orbital. So it's not really like, and so if you think about it in terms of the energy, 1 electron at the low energy state, 1 electron at the high energy state averages out to the middle, right? So basically, by shining light with the right frequency on it, we're promoting an electron from the bonding to the anti-bonding orbital, which causes a homolytic cleavage. If it's a heterolytic cleavage, then either these are offset so that they're not starting at the same energy. That allows 2 electrons to go one way instead of the other way, and no electrons the other way. But if these are the same energy, promoting that electron gives you that homolytic cleavage. And the other way you get heterolytic cleavage is when you bring in outside electrons, because that allows everything to stay in its ground state, it's more in its lower energy state, and that allows the electrons to move as a pair rather than splitting up. Another note as far as notation goes, a pi bond, we just write the Greek letter pi. If we want the shorthand for a pi anti-bonding orbital, it's pi star. A pi star bond is the pi anti-bonding orbital, corresponds to the pi orbital. And same with sigma star. If this is a sigma bond down here, this is a sigma star. This is the shorthand to mean anti, but without using negative signs, because we don't want to confuse that. So in terms of halogens and oxygen, this gap between sigma and sigma star is low enough that UV light can break it apart. With carbon-carbon bonds, the gap between these is much higher. That's why we don't really see, if you just shine UV light on carbon molecules, you don't see free radical reactions happening. It has to have an initiator molecule in there that where you can get to that difference in energy with the light that you have. If we had super high energy photons, if we're talking, gamma rays, X-rays, things way, way up there in the energy scale, you can actually just use light to blast carbons apart. And then, but then you don't really have predictable reactions, you just have everything flying apart. And same's true if you heat something to the point that it becomes a plasma. The definition of a plasma is one, it's a supercritical fluid, but it's also that your electrons have so much energy that they're not actually bound down here anymore. They have enough energy to freely move between the bonding and the anti-bonding. And they have enough energy that they can actually freely just leave the nucleus. So plasmas are a totally different thing. If you get high enough thermal energy, then bonds aren't holding things together anymore. That's part of why things are easier to break apart at high temperatures. Why you get so many competing reactions. For carbons though, at Earth-like conditions and temperatures, we don't really see this happening because we don't have access to photons that are high enough energy and we're not at high enough temperatures to worry about sigma bonds breaking. But pi bonds, their pi orbital and the pi star orbital are close enough in energy that we actually can wind up with UV or visible light in some cases, actually promoting electrons to high enough levels. So we can break pi bonds
relatively easily with light. And it doesn't always necessarily result in, because we're not breaking the sigma bond, usually what will happen is they'll just wind up reforming. So we don't really get free radical reactions that way. But it does give us a way that we can get past that S cis to S trains pretty easily. We just need the right wavelength of light to temporarily break one of those pi bonds. Or promote an electron to an anti-bonding orbital, and then it will twist freely, and then it will just reform that same. Right, the reason that breaking a sigma bond results in a free radical reaction is because once you break a sigma bond, there's nothing tethering those two atoms together, so they have a decent chance of just each atom goes its own way as a radical. We don't have that here because these atoms are forced to stay next to each other because the sigma bond is still there. Right, and so looking at it in terms of sigma bonds or pi bonds for an isolated alkene is this simple. When you bring them up together, you get constructive interference and destructive interference, you get a bonding and an anti-bonding orbital. However, the more pi bonds you bring together, the more p orbitals you bring together, the more possible ways you have of combining their p orbitals. Right here, they either have to be in phase or out of phase. If you flip a coin once, you're either heads or tails, right? It's better combinations. If you flip a coin twice, they're either both heads or both tails, or the mismatch, right? There's only two possible outcomes. They're in phase or out of phase. When you do that 4 times, it gets a little trickier. Right, and so I'm going to keep going over here because I don't want to make this graphic too much smaller. To fit on the board there, I guess. We'll just put that. All right, so if we have 4 p orbitals, we have a total of 4 electrons as well, right? And the lowest energy state would be no nodes, or the only node is between the blue and the red, top and bottom. But there's another state that still has more constructive interference than destructive interference. If you had 1 node right in the middle, it still kind of looks like two pi bonds. They're out of phase with each other now, so you have less resonance to do that. But that still looks like more bonding than non-bonding or anti-bonding. But then you could also have 2 nodes in there. So blue top, blue bottom, blue top. Adding 2 nodes is going to be higher in energy. And it's not quite linear, but it's close to linear as far as how these energies scale. They're pretty equidistant from each other. Everything matched up, all blue on the top, all red on the bottom. 2 match up. This one looks like 1 pi bond and then 2 isolated out of phase p orbitals. So that's going to be higher in energy. That's not a complete non-bonding orbital or anti-bonding orbital, but it's close. There's more anti-bonds, there's more nodes than there are bonds. And then the highest energy case is if it alternated every single time back and forth. Then you have no pi bonds. And you have only anti-bonds. Oops, right.
These are all like existing in a superposition.
Correct.
So it's not like.
Correct, but this is why it's low enough in energy. One, so this actually looks a lot like our resonance structures that we drew, right? It's higher in energy, but it still has a pi bond in there. Actually breaking across that middle one, we actually have to go up in energy to do that, to get it to rotate. All right, and so this led to another Nobel Prize winner. This is one of the reasons this is a fun quarter to teach, is we get to actually talk about more recent Nobel Prize winners. Kenichi Fukui won the Nobel Prize in 1981 for research that he had done almost
I want to say it was more than 30 years earlier. Usually the lag time on a Nobel Prize is, if it's really big, a really big advancement, might be as soon as 10 years after you did that. If you look at the most recent one I can think of was the Nobel Prize in Medicine for mRNA vaccines during COVID. They had already done the research for those mRNA vaccines 10 years earlier. It took them 10 years and a pandemic of pressure to actually get it to work reliably in humans, but they demonstrated in mice back in 2012 or something like that. And that's about the shortest turnaround I've ever seen for a Nobel Prize, is 8 to 10 years. It took Fukui 30 plus years to get recognized. And even then he had to share it with American scientists. And if you look at the timing, it's almost certainly because he was Japanese. And Europe and America did not feel kindly about the Japanese post-World War II. So it's almost certainly due to racism, because the people that actually did the research they get to share with, usually if you're sharing a Nobel Prize, it means that you did your research at approximately the same time. They were about 10 years behind them, but they were American. So it's worth noting that Nobel Committee, it's kind of like the Oscars in that sometimes it lags behind, and there is politics that go into it as well. I mean, right, look at Mendeleev. Mendeleev never won a Nobel Prize, and he invented the periodic table because nobody liked it. So Fukui, and not to say Fukui was a perfect person either. He did work on he did chemical research for the Japanese army that was involved in some pretty horrendous things during World War II as well. So he's far from a perfect person too, but if we're holding all scientists to that standard, then nobody who was in World War II should have gotten a Nobel Prize. In terms of crimes against humanity and whatnot. So, all that to say, he came up with this idea of frontier orbitals. Frontier orbitals was what he referred to as the HOMO and LUMO, the highest occupied molecular orbital and the lowest unoccupied molecular orbital. He basically put forward the idea that the HOMO and the LUMO dictate reactions. By moving electrons around between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, that's going to actually be able to explain a lot of your reactions, just like we did over here. Our highest occupied molecular orbital was a sigma bond. By moving electron density into the lowest unoccupied molecular orbital, we can get that bond to break. It is. That's why we go with frontier orbitals is actually a pretty good way to describe that, because frontier, the edge of what is occupied and unoccupied. Right, and so this, we wind up seeing some interesting things happen with this, with these orbitals when we start looking at different temperatures. And so this is actually one of our classic examples. This should look, the second step here, should look pretty similar to one of our labs, right? Our thermodynamic control versus kinetic control. Because the blue line, the 1,2 adduct, is favored kinetically in terms of rates. But the 1,4 adduct is favored thermodynamically. And so the 1,2 adduct, if we're looking at this, the addition reaction here, the 1,2 adduct is just our classic example of a hydrogen catalyzed, acid catalyzed bromination. Right, you're gonna add a carbon hydrogen bond to the less substituted carbon. Your intermediate's gonna look like a carbocation. Now I want to draw. So how do you get the 1,4 adduct? from the resonance structure. So our first intermediate would look like this. That's gonna give us the 1,2 adduct. If it goes through a resonance structure, we get a positive charge on a primary carbocation, which we would normally think that's unfavorable. Right, that is unfavorable, that's a higher energy state to be in, right? So this is a minor contributor to the resonance. But if you look at the final product, the 1,4 adduct made the more substituted alkene, made the Zaitsev product. So even though the transition state is going to be less favorable, the transition state is less favorable because we have to go through this resonance structure. But the final product is more favorable because it's Zaitsev's rule. Alright, so we always have to be thinking about that when it comes to these. When it comes to these conjugated dienes, it's not a new concept, we've talked about it in the past. But now is where resonance is really gonna start playing a role in how we do this. And it's a good preview as well for where we're going next quarter, because we are gonna start off with aromatics. And resonance obviously is gonna play a big role in how aromatics react. What makes them aromatic in the first place is a lot of these orbitals and resonance ideas. All right. So for this product, what are the two possible products? And then which one is the thermodynamic product and which one is the kinetic product? And I guess we actually going to have 4 products here, right? That's asymmetric. We can get the 1,2 adduct plus or R plus S. That's the 1,2 adduct if it reacts with the top pi bond. The 1,4 adduct if it reacts with its top pi bond is going to look like this. R plus S. All right, so those would be the ones that went through the intermediate that looks like this. And its corresponding resonance structure, which is going to look like this.
There's also going to be a resonance structure just from the initial product, right? There's a double bond on the right side of the hexagon, positive charge on the tertiary.
Correct.
That's what I started.
So there is a resonance structure just from this.
Yeah.
However, because, so if we draw that one out. And it's gonna be, there's gonna be a symmetrical one as well. You could think of this resin and the one with the charges flipped. You can think of this as being why you protonate this carbon or that carbon as your first step, because there's a partial negative. So it's attractive to a positive hydrogen ion. However, I was just approaching it from the point of view of our regular acid catalyzed
hyperbromination.
So it's safer to do the proton transfer first and look at that.
And then look at that resonance structure. We'll get to where that other resonance structure winds up being important for another class of reactions that we'll hit next class. If we looked at it, the bottom reacting first, our resonance structures then, or our intermediate rather, would be, we added a hydrogen here, so a positive charge there. And then the resonance structure would then look like that. So in these resonance structures for our intermediate, any spot that has a positive charge on it is going to be an attractive target for a nucleophile, right? So we wind up adding bromide in all those positions. Once again, this is the 1,2 adduct. And then we will also get the 1,4 adduct. It's going to look like that. Again, R plus S. So 4 possibilities. Which makes sense, we have 2 ions, right? So there's 4 different ways we could do that. Which one is going to be? So, and we can do a kinetic and thermodynamic for the blue and a kinetic versus thermodynamic in the purple as well. Right, in both cases, in all these cases. The 1,2 adduct is going to be the kinetic product. It's especially easy to see for the blue example, because one of our carbocation intermediates is tertiary versus secondary. Here it's a little bit less strongly in favor. They're both secondary. And so the kinetic versus thermodynamic product is not going to be as big of a difference here. Especially considering both of these have equally substituted. It leads to an equally substituted alkene in the end, right? So Zatev's rule is less of a factor. And they're both going to be close to the same kinetically. We'll still favor, under kinetic conditions, we'll still favor the 1,2 adduct, mostly just because of proximity. If you had to add a bromine or a hydrogen here, then your bromide is already close to that carbon physically. But it's a lot when both of the carbons are secondary and both of your alkenes are equally substituted. It doesn't matter as much thermodynamic versus kinetic control. This one is going to be favored craftway because we get that thermodynamic or that tertiary carbocation as a resonance structure. So that means these under thermodynamic or kinetic conditions, the blue molecules are favored. And we can tweak whether or not we see this product based on temperature. Low temperature is going to favor. So out of these, which is thermodynamically favored and which is kinetically favored? This one's going to be the kinetically favored because it's going to have that lower barrier, putting a positive charge on a tertiary carbocation. And because of the proximity effect. This one's going to be thermodynamically favored because it's the more substituted alkene. So
let me erase the purple ones now, so we're not confusing ourselves, since it's less of an issue with the purple ones. So kinetic. Thermal. And if we are. I guess I should color code it for the sake of being able to. Verbally answer. So anytime we have a difference between thermodynamic and kinetic product, that means we have this crossover. So which one is the kinetic product? Red or purple? Red. Lower transition state barrier gives you your kinetic product. So purple is our thermodynamic product. If everything has enough energy to move back and forth, then you're going to wind up with this one in equilibrium. So at low temperature, do we favor the kinetic product or the thermodynamic product? Kinetic product. At low temperature, not enough has energy to make it past this barrier. So you're limited to only going on the red pathway.
So just think about that, it's like intermediate, it's like most stable intermediate, kinetic, it's just lower variant.
Correct.
Opposite, you said that less favorable resonance structures are more favored at higher temperatures.
I hesitate to make a generalization about that. In the case of conjugated dienes, yes. Because with conjugated dienes, the less stable resonance structure is going to give you the more substituted alkene. So for this particular part of this chapter, yes. All right, and so the way that we indicate this, we'll finish up here just this last slide, and that leaves us in the perfect spot here. Is basically, we're just going to define 0 Celsius as low temperature, and usually 40 Celsius gets for these reactions is high temperature. So 0 Celsius, going to make our kinetic product. 40 Celsius, give us a thermodynamic product. And as we saw with our thermodynamic versus kinetic lab, we do get a bit of a mixture depending on how big of a difference it actually is. If they're close to the same energy, if it's not a strongly favored thermodynamic product and a strongly favored kinetic product, we can get a mixture of both, but we'll favor one or the other based on the temperature. All right, so 0 Celsius favors the red line, 40 Celsius, the purple line. And then next class, we'll get more into orbitals. We'll talk about what are called pericyclic reactions. So basically, I wanted you to be thinking about these orbitals and nodes and pi bonds. So that one, we can talk about resonance a little bit, but also to sort of set the table for this next class of reactions, because that's actually where these frontier orbitals and the HOMO versus the LUMO are really going to play a role. We'll actually get the opposite thermal or the opposite stereoisomer of our product, depending on did we catalyze it with heat versus light. Because heat means that it goes through the HOMO, and light means it goes through the LUMO. Right, and so we'll talk about that in all these reactions on Thursday, assuming we have school, then next Tuesday if not. All right, so we have about 1 lecture worth of material left to go over. It does look like a coffin, huh? Cycloadditions, electrocyclic reactions, and sigmatropic rearrangements are all pericyclic reactions, and that just sounds like a bunch of gibberish right now. All right. So just a reminder also, if you haven't, come up with what molecule, and you can talk amongst yourselves once you submit your suggestions for what molecule we should replace the cinnamaldehyde with. But I want us collectively in two groups to try at least two other molecules. If we want to do more, if we have 3 good candidates or 4 good candidates for last week's lab, then we can all do our separate ones, but we want to try and get a couple options. So think about that. Talk amongst yourselves between now and 1.
Trying to pick the spreadsheet for each.
Did it not work for you?
No.
Was thinking just do warning, sulfurine, and both of those should work, and resonance may be a problem.
Jerry, you had an idea too that was not one of those other 2. So I was thinking we had at least 3 proposed.
Oleic acid.
Oleic acid. Yeah, fatty acids might work too, because they're isolated. Most of your fatty acids are not most of your unsaturated fatty acids are not conjugated.
It's very
Yeah.
isolated.
Very isolated.
Very isolated.
So oleic acid is a good example. So we have 3 good ideas there.
And the product should be above 50 Celsius for the melting.
65.
Yeah. All right.
I mean, if you're adding bromine, it should technically raise the.
Yeah, the product from sulfurine is 0.6 is a lot.